On your wrist, a small machine keeps near-perfect time. No winding, no swinging weight. Just a sliver of crystal, humming faster than you can imagine. A good quartz watch drifts less than a second a day, year after year. So how does a chip of rock, a battery the size of a lentil, and a few tiny gears all agree on exactly what a second is? Let's slice one open and watch a single second get built, step by step. To keep time, you need something that repeats at a perfectly steady beat. A pendulum swings. A balance wheel rocks back and forth. Each tick must match the last, or the clock slowly wanders off. The trouble is that springs sag and warmth shifts their rhythm, so watchmakers went hunting for a better metronome. They found one hiding in quartz, the same mineral in ordinary sand. Inside it sits a beat so fast and so even that counting it gives us a second we can truly trust. It begins with the battery. A quartz watch carries a tiny silver oxide cell about the size of a lentil. It pushes out roughly 1.5 volts, a gentle, steady trickle of electricity. That trickle is the whole power budget. It must run the crystal, the counting circuit, and the motor for years on end. Because every part sips so little current, one small cell can last 3 to 5 years before it finally runs flat. Power is in. Now we need a beat. At the heart of the watch sits the quartz itself. Engineers cut it into a tiny tuning fork, thinner than a hair and just a few millimeters long, then seal it in a metal capsule to keep out air and dust. Quartz is special because it is piezoelectric. Squeeze it and it makes a small voltage. Apply a voltage and it physically bends. That two-way trick is the key. It lets electricity and motion talk to each other inside a single sliver of crystal. Here is where the beat is born. The battery feeds voltage to the quartz fork and the fork flexes. As it springs back, the strain makes its own tiny voltage, which the circuit senses and feeds right back in. Push, flex, return, push again. Like a child pumping a swing at just the right moment, each nudge lands perfectly in time with the crystal's natural rhythm. Within an instant, the fork settles into a clean, relentless vibration, and it simply will not stop. And that vibration is astonishingly fast. The fork is shaped to flex exactly 32,768 times every single second. That number is not random. It is 2 multiplied by itself 15 times, a tidy power of 2. You cannot hear it and you cannot see it. The motion is microscopic, but it is far steadier than any swinging pendulum, barely nudged by gravity, by position, or by a bump on your wrist. This is the metronome the whole watch will trust. Keeping that beat alive is the job of a small circuit etched onto a chip. It does 2 things at once. First, it feeds the fork just enough energy to replace what friction steals away, so the vibration never fades. Second, it shapes each soft swing of the crystal into a crisp electronic pulse, on and off, on and off. Now the gentle hum of quartz has become a stream of clean digital ticks, 32,768 of them each second. But 32,000 ticks a second is far too fast to move a hand. So the chip counts them down. A chain of digital switches, called flip-flops, each cut the rate cleanly in half. Halve it once, then again, 15 times in a row. 32,000 becomes 16,000, then 8,000, then 4,000, on and on, until what comes out the far end is exactly 1 clean pulse every second. The fast, invisible beat has been folded into the tick we actually want. That 1 per second pulse now needs to become movement. It flows into a stepper motor, a clever little engine smaller than a pea. Inside sits a coil of fine wire wrapped around a metal core, facing a tiny magnetized gear. Each pulse flips the current through the coil, and the magnetic field flips with it. The little rotor snaps a precise half-turn, then waits for the next one. 1 pulse, 1 step. This is the moment electricity finally turns into the visible motion of time. From the motor, the steps travel through a train of gears. The first wheel turns once each second and drives the sweep of the second hand. Its teeth mesh into a larger wheel geared 60 to 1, so 60 steps nudge the minute hand a single notch. Another set divides again by 12 for the hour hand. They are the same simple ratios a clockmaker used 3 centuries ago, only now they are driven not by a coiled spring, but by a humming crystal. So why trust quartz over springs? Because its beat barely cares about the world around it. Temperature can nudge the rate a little, so the fork is tuned to run truest, near the warmth of your wrist. Even then, a good watch drifts only a few seconds a month. To do better, makers sometimes trim the circuit, quietly dropping a stray pulse now and then to cancel the error. It is not perfect, but for a sliver of sand, it is extraordinarily close. So follow the whole chain one more time. The battery sends a steady trickle of voltage. That voltage drives the quartz fork, which flexes 32,768 times a second. The oscillator circuit keeps that beat alive and sharpens it into pulses. The divider folds those pulses down to exactly 1 per second. The stepper motor turns each pulse into a single step, and the gear train spreads those steps across the second, the minute, and the hour hands. A chip of rock, a lentil of power, and a handful of gears, all quietly agreeing on what a second is. The next time you hear a watch tick, you will know the silent, racing hum behind it, folding a microscopic beat down into the steady march of a hand. So much hidden inside something so small. That's one more everyday thing, sliced clean open.